Okay, good. Okay. So, again, it's kind of like that saying, we can learn a lot about a function from its graph. Okay? In particular, we can determine when a function is increasing or decreasing. The idea with increasing is if we increase the input, then for a function to be increasing, the output has to get larger as well. So as the input gets bigger, the output gets bigger. That's for a function to be increasing. Graphically, the graph has to go up. You have to move northeast. Or if you want, the graph has to rise. That's better. It's climbing. Whereas it's decreasing if instead, as we increase our input, visually to increase the input, you move horizontally to the right. To be decreasing, the output gets smaller. The graph falls. It's moving southeast. Okay? And it's constant if it doesn't go, if the outputs don't change. If the output is not changing, then the graph is not rising and it's not falling. It's horizontal. Now, just to illustrate that, let's look at this example. Notice that as I move to the right, okay, moving horizontally to the right, you can see that the numbers are increasing, right? What's the graph doing? Well, this wonderful graph is climbing, right? We're moving up, northeast. So because of that, this graph is rising. So the function is increasing. And again, your height, how high above or below, that's what the y values are. That's the height. Whereas with this graph, as you move horizontally to the right, what's happening? This graph is falling. As you can see, it's going down. I know as you go further out, it looks like it's not falling, but it actually still is, although it's kind of hard to see it. But so from the graph, we can see this function, as we move to the right, it's decreasing. Okay? So we have that example. So we have those two examples of functions that are increasing and decreasing. Again, we don't know what the formulas are, but we have the graphs. So from what we see, we have this. Okay, that was fun. In fact, it was so much fun. Let's do another example. So here's another one, right? So again, as we move horizontally to the right, where our input, our horizontal axis, the x, is increasing, what's this graph doing? It's going up. It's rising. You can imagine if you were walking along the graph, right? You're getting further away. You're going higher and higher, that is. So that tells us the function here, it's increasing. It's in, oh boy, sing. Excel. And again, you can imagine walking along it. Remember, like you're moving up and to the right, northeast, as you walk along it. Here's another fun example. In this case, as you move to the right, as you're increasing x, what happens here? You're moving down towards the right, southeast. The graph, in other words, is falling. So this wonderful thing is decreasing. So we have this example, okay? You know, again, you can imagine walking along the graph. You can see that you're moving, that the graph is falling. You're walking down and to the right. Hence, your y values are getting smaller. Now, for this one, right, we'll notice that as we walk to the right here, if I can, where's the mouse? There it is. Right, as we walk to the right, as you can see, what's happening here? Well, here, the graph starts out decreasing, right? We're walking down towards the right. The graph starts out falling, but then it's going to start increasing. So it starts out decreasing, but then it's increasing. So you could do one or the other. You can't do both, of course, but you could do one or the other. So that's what we have here. Okay, so that's an example we have. That's good. Okay. So we have an increasing, a decreasing, and a function that's doing neither. But it's not constant either. So it starts out decreasing, then it becomes increasing. Now, this is something also, let me just say this, that a vertical line is not the graph of any function. Okay, you might know already why. If you don't, that's okay. I know if you had me for Math 104, I went over why that's the case, but it's good to know that a vertical line is not the graph of a function. I mean, intuitively, what's going to happen is you'll have a certain x that gives you infinitely many outputs. So you're not going to have just one output. Okay. Okay, that thing is down there, but let me just say this, so just ignore this if you can. So for now, but we can have a special kind of function, a linear function. That's a function whose graph, it's a non-vertical straight line. So if you actually go back to these examples, these are linear functions because their graphs are straight lines and they're not vertical. Whereas this, it's not a straight line, so it's not vertical. So it's not linear, but these are. Now, okay, so they're linear. What does that also tell us? Well, you probably have seen, if you haven't seen lines before, that's okay. But it turns out any linear function can be written in that form. Any linear function can be written as f of x equals mx plus b. You might also see y equals mx plus b. You could also see that. But any linear function can be written like this. B is just the value of the function at 0. That's just, hopefully it's easy to see. The m is very important. On the one hand, it's called the rate of change. I'll tell you why shortly. It's also called the slope of the function. It's also called the slope of the function. The slope of the line. That's better. The slope of the line. That's what m actually is called. And yes, it's calculated down here, as you can see. We'll get to that shortly. Okay? But this is just what I said before. The slope of a line is also called its rate of change. Okay? And to actually calculate it, I mean, this is one way of looking at how to calculate it. You subtract two outputs divided by the corresponding inputs, or you could think of it this way. If the linear function, if the line passes through these 2 points with different x values, then you can get the slope this way. You know, change in output over change in y over corresponding change in x. Same thing over here. So we can get, so the slope and rate of change of a linear function, it's just the same thing as it's for a line, it's just the same thing as it's for a line. And again, the line has to be non-vertical. Okay, that's fun. That's good. Well, And this is something else I threw in here, that any non-vertical line, the graph looks like this. Okay, I'm probably saying more than necessary, but this is one example. So this is an example of a linear function. In this case, I'm not sure what b is, but this is where that point 0b would be. So, okay. All right. Now, to get an equation of a linear function, or actually I should say a line, you could use this. If you want to stick with this, that's fine. I just threw this in here just for completeness, but I guess you really don't have to use it. But you could also use this if you want. This is where the point AC is any point on the line. This is actually what they call the point slope formula. This is actually called the slope-intercept form, point slope form, slope-intercept form. M is the slope of the line, but here you can have AC as any point on the line. So it's a little bit more general than this. But if you want to stick with this, though, that's fine. I know this can be a little tricky, I understand. And here, all I'm trying to show you here is why the slope is a rate of change. We'll do an example shortly. I hope this makes sense. The idea is if you were to increase your x by 1 unit, if you increase your x, your input, by 1 unit, whatever a unit is, unit could be feet, meters, whatever. What happens is your y coordinate, your height, will change by m units. So your y is going to change by m units. That's why it's called the rate of change. For each unit change in your input, your output changes by the slope. Okay, let me just, hold on. Let me, wait, no. 1 second. Let me just, 1 second. I just got to pause the recording. I'll put it back up. Don't worry.